Hi and welcome to this video on applications of differentiation. When we're talking about applications of differentiation, let's first go over some of the terms used. So if we have a curve which is f of x, this is a positive slope if we draw a tangent to the slope, so this is positive. If the tangent to the curve is going downwards, this is a negative slope. This is an inflection point. Let's go up a little bit here. Where we have the gradient or the slope going in a negative direction, then to 0, and then in a positive direction, this is called concave up. And then the opposite, where the rate is going up in a positive direction and down in a negative direction after going to 0, this is called concave down. This is a maximum, and this is a minimum. So what we do when we want to find out more about the curves, or in applications of curves, we do a first derivative test. So say we had a function f of x, x to the power 4 minus 2x squared. So we would look at the critical points. So how do we get the critical points? So to get the critical points, we find the first derivative. And the first derivative, or f dash of x, is, bring the 4 down, 4x to the power 3 minus, bring the 2 down, multiply by the 2 is 4, and then x. Now, to find the critical points, we set this to 0. So 0, and we factor first. Critical point set to 0 after factoring. So 0 equals 4x x squared minus 1. So we have 4x equals 0, and because this is a difference of squares, we have x squared minus 1 equals 0, and x squared plus 1 equals 0. Therefore, we have x equals 0, x equals plus 1, and x equals minus 1. And these here, 0, plus 1 and minus 1, are our critical points. Now when we look at our critical points, if on approaching our critical points we have a negative gradient, then the critical point, and then a positive gradient, this is a local minimum. If we have a positive gradient and then the critical point and then a negative gradient, this is a local max. If we have a plus and then the critical point and then a plus gradient, this is neither. And then the same if we have a minus and a minus, it's neither. To find these minus and plus gradients before we reach the critical point, we draw a number line, but we put our critical points on the number line, so we would have -1, +1 and 0. Those are our three critical points. This would go to -infinity and this would go to infinity. Then what we do is we test the four intervals that are between the critical points. So we choose numbers between the intervals, say -2, minus a half here, a half here, and say 2 there. So those are our test points or our test intervals, and then we plug these into f dash of x, which was our derivative, and see if they're positive or negative. So what we get here then when we test, let's draw a number line again, 0, -1, 1. When we put in -2, -half into our derivative, which is over here, f dash of x, first of all we get a negative, so we do a downward arrow, then we get a positive, at 0 it's 0, then we get a negative, and then we get a positive. So this tells us that in our original curve we have a concave up going to a 0 and then another concave up, like so. An easier way of finding whether the curve is positive or negative at a point is to do the second derivative test. Now the second derivative test is nothing but d by dx of dy by dx. So this becomes the second derivative. And what this tells us is, say we've got a concave up curve, so this is going from a minus to a plus. So the gradient is going from a minus to a plus. So if the second derivative is greater than 0, it's a minimum, or it's a concave up curve. Similarly, if the second derivative goes from a positive to a negative gradient, i.e. it's less than 0, then it's a maximum, or it's a concave down curve. Now quite often we can be asked in differentiation and applications of differentiation to find tangents and normals. So let's go over what a tangent is. So if we have a graph of a curve, so that's the curve, which is f of x, and a point on the curve where x equals 3. Then the tangent to the curve would be the gradient at that point where x equals 3, and it would be something like that, which is the red line. So that would be the tangent at that point to the curve, and then the normal is 90 degrees at that point to the tangent. So the green one is the normal. Now when we're asked to find tangents and equations of tangents, we use a very important equation, which is y minus y1 equals m, which is the gradient at that point, x minus x1. So this is a very important equation that you need to memorize. Put it in a red box. The normal, which is at 90 degrees to the tangent, is simply the same y minus y1 equals m, but in this case m is the negative reciprocal, so it would be minus 1 over m x minus x1. So this is for the tangent and this is for the normal. So let's go over an example. So say we had y equals x squared plus 1. So first of all we need to find our y value. So x was 3, so let's put in x. So 3 squared is 9 plus 1 is 10, so our xy becomes at that point 3, 10. Now we want to find our m, so to find m, which is the gradient, we differentiate, so we get dy by dx, bring the 2 down, and x, and then power minus 1, just leave it, it becomes 2x. Now when we put our x equals 3 into here, we get 6. So we're putting the x equals 3 into our equation, our differentiation equation, which is 2x, and we get 6. So this is our m value in the equation, and that would be for the tangent, and for the normal it would be minus 1 over 6, the negative reciprocal. So let's now use our formula to find out the equation of the tangent. So the equation of the tangent y minus y1, so that's y. y1 was 10, equals m, which we found for the tangent is 6, x minus x1, which was 3. So this then, when we get rid of the brackets, becomes y minus 10 equals 6x minus 18. And on rearranging our formula, then, or our equation becomes y equals 6x minus 18. For our normal, equation of normal, we simply put our m for the normal into the equation, so we get y minus 10 equals minus 1 over 6 x minus 3. So this then becomes 6y minus 60 equals minus x plus 3 x plus 6y minus 63 equals 0. And those are our equations. That's for the tangent, and that's for the normal. This should have been minus 18 plus 10, which is minus 8. Another application of differentiation is in optimization. In our approach to optimization, first of all, step 1, we set up two equations. The first equation is usually called the constraint equation, and we are usually given something which makes the constraint equation. So for example, we're given a volume as being, say, 200 centimeter cubed, or we're giving a surface area or something like that, and we make a constraint equation. And the second equation is usually the optimization or minimization. And this is usually like a sum of all the surface areas, or a sum of all the sides to make a length, or something like that. And now what we do is step 2. We plug one equation, and it's usually the constraint equation, into the optimization equation. And you should be left with only one variable. And then step 3, we take the derivative, set equal to 0, and solve. And if we apply those steps, it should make it easier for us. So we'll go through a few examples using steps 1, 2 and 3. Then we want to make a waste paper basket, which is an open cylinder, volume 2000 centimeter cubed. Find the radius of the base if material used to be is minimized. So let's draw a quick diagram. So our bin is going to look something like that. Cylindrical, open at the top. This height is h, and then from here to here our radius is r. So first of all we have a constraint equation where they tell us the volume to be used is 2000 centimeter cubed. So what's the volume of a cylinder? It's the area of the disc or the circle at the bottom, which is volume equals pi r squared h, and that equals, we're told, 2000. So the other thing we need is the surface area. So our surface area is pi r squared, which is the surface area of the disc at the bottom, plus we want the surface area of this rectangular piece at the top, which would be pi r squared plus 2 pi r h. Two pi r being the circumference and h being the height. Now we've got the surface area and the v. We want to put the v into the surface area equation, and we can do that and eliminate h. So let's make h equal, and we can do that by making 2000 to the top and divide by pi r squared. So now our surface area equals pi r squared plus 2 pi r, and then our h simply becomes 2000 over pi r squared. So let's see if we can simplify this in some way. So we've got pi r squared plus one of these r's and the pi r can go, and then 2 multiplied by that gives you 4000. So that's 4000 over r. So we go with that, 1 r remains, and that 2 times that is 4000. So pi r squared plus 4000 over r. So that's our surface area. So now we differentiate. So we have ds by dr equals, bring the 2 down, 2 pi r, and then we have minus, when we differentiate it, taking the r as r to the minus 1, we have minus 4000 over r squared. Now we set this to 0, which is our next step. So 2 pi r minus 4000 over r squared equals 0. So when r squared, when we bring the r squared up, or we multiply both To get rid of the r squared, we multiply by r squared and multiply this by r squared. We get r cubed equals 2000 over pi so r is cube root of 2000 over pi. If we take the second derivative, we want to test that this is a minimum. The second derivative being d to s over dr squared, we get 2 pi plus 8000 over r cubed, and this is positive, so it is a minimum. And when we work out r 2000 over pi and the cube root of that, it's approximately to one decimal place 8.6 centimeters. Okay, in this question we want to make a rectangular block, surface area 150 centimeters squared, and we want to know what the dimensions of the block to maximize its volume. So let's draw a quick sketch of what we're talking about. So we're talking about a rectangular block, like so. So coming out here, like that. This is x, and this is h. Okay, so we're given our constraints, which is the surface area is 150 centimeters squared. So surface area for this block would be, so we would have 2 by x squared, so x squared would be the top surface and the bottom surface, 2 of those, plus, and then we'd have 1, 2, 3, 4 sides, which is 4xh, and that would equal 150. And now what we're trying to optimize is the volume, and the volume, that would equal x squared, so this is x times x, which is that, and then we multiply that by the h. Now what we need to do is get rid of one of the variables, because we've got 2 variables here, so we can make h the subject of the surface area. So let's do that. So h, 2x squared plus 4xh equals 150. Divide through by 2, we get, so when we divide by 2, we get x squared plus 2xh equals 75. Then bring that to the other side, we get h equals 75 minus x squared all over 2x. So now we can put this into our equation that we want to maximize. So we get the volume equals x squared, which is over here, and then the h, which is 75 minus x squared all over 2x. Now, how can we simplify this? Well, if we think of this as a complex fraction, we can divide that into 2, we can divide this into 75 over 2x minus x squared over 2x. And now if we get rid of the fractions, so this becomes x squared a half 75 x to the minus 1 minus a half x, multiply that through by x squared, and we get a half 75x minus a half x to the power 3. So this is our v. Now we can differentiate, having found v in terms of one variable. Let's do dv by dx. And that equals 75 over 2 minus 3x squared over 2. So if we set this to 0, so 75 over 2 minus 3x squared over 2 equals to 0, then when x squared equals 25, it'll be 0, which is x is plus or minus 5, which is the square root of 25. So our length cannot be a negative, so it has to be a positive. So we can test that. So if we put x equals 5 into our differentiation, which we do twice, which is d2v over dx squared. This is minus 6x over 2, which equals minus 3x. So if we put that into 5 into there, we get a negative value. We don't have to actually work out the value, we just need to know whether it's negative or positive. And because it's a negative value, that means it's a maximum. Here we want to find a pair of integers so that they have a product of 196, and then we want to minimize the sum. So this is our maximum and minimum, and this is our constraint of 196. Minimize the sum of the numbers where 4 times the first number is the second number. So our constraint is the sum x, y equals 196, and the one we want to minimize is the sum, which we'll call s, is 4x plus y. So we want to put our constraint into this, so we need to work out what y is. So y equals 196 over x. So we put, now the sum is 4x plus 196 over x. If we write this into something we can differentiate, we get 4x plus 196x to the minus 1. Now let's differentiate, so we get s dash is 4 minus 196 over x to the power 2. Let's now make this into a 0. So that's 4 minus 196 over x squared equals 0. So we have 196. This will equal 0 when 196 over x squared equals 4 to make this whole lot 0. So 196 over x squared equals 4. So x equals, or x squared equals 49, and x will equal plus or minus the square root of 7. So we can't have negative 7 because that's not an integer. So the answer would have to be 7. So let's just test that by using our number line. And we'll put 7 in the middle. And if we put our, say, a number into here, we get a positive or a negative. So let's do that. So if we put a number into there, 4 minus a large number would be negative. So that will go down here, so that's negative. And then if we put a number larger than that into there, that would be positive. So this would mean that 7 is a relative minimum. So let's have a look at this problem. We're trying to maximize the rectangle within these constraints below the line y equals a. So what are we looking at here? So if we draw this parabola, y equals x squared, it's something like that, goes through the origin and up, and we've got a rectangle in here, and this is the line y equals a, and we want to maximize the area of the rectangle below that line. So the first thing we have to realize is that this point here is nothing but x, and because we're looking at y equals x squared, so this point is nothing but x squared. So the area equals, because this is x and x on both sides, 2x, and then we multiply that by a minus x squared. So that would be that value of y minus that value of y to give us the total length, or the height there. So that's the area we've got in algebraic form. So when we multiply out, we get minus 2x cubed plus 2ax. So the area equals minus 2x cubed plus 2ax. When we differentiate, so we get a dash would equal minus 6x squared plus 2a. We get that to equal 0, so minus 6x squared plus 2a equals 0. So that means that minus x will equal the square root of a over 3. So this is a critical point. Square root of a over 3, and our area, or the max area, will be given by this 2 a square root of a over 3 multiplied by 2/3 a. A wire of length 28 meters is to be cut into two. One piece is made into a square frame and the other a circle, and we want to know what the length of the two pieces should be so that the combined areas of the two frames is a minimum. So what we're doing is we're getting a length of wire there, and we're going to cut it into two. So let one part be x and the other one would be 28 minus x. So the x we're making into a circle, and this one we're making into a square. So x equals, the perimeter of the circle is 2 pi r, and the 28 minus x, that equals the perimeter of the square, which if we call it a, is 4a. Okay, so in this case we get a equals 28 minus x over 4, and here the radius r equals x over 2 pi. Now the sum of the areas, which is what we want to minimize, would be pi r squared plus a squared. So total area is pi r squared plus a squared. So we want to get rid of these variables, so we've got what r is in terms of pi and what a is in terms of x, so we can make this in terms of x and pi. So we have area equals pi, and then we put the r, which is x over 2 pi all squared, and plus our a, which is 28 minus x over 4 all squared. Now let's get rid of the brackets if we can, so simplify it a little bit. This becomes x pi over 4 pi this should be x pi squared is x squared, or pi x squared, plus, and we get this 78,784 plus x squared minus 56x all over 16. So here we can do some cancelling out, so we get the pi squared and the pi going out, so that just leaves pi here, and we get that goes out there, leaving the pi there, so this leaves us with x squared over 4 pi. And now we can split this fraction up into 3 because we've got addition and subtractions onto here. So this becomes 784 over 16 plus x squared over 16 minus 56x over 16. Now we can differentiate. So we have dA over dx. This becomes 2x over 4 pi plus, that's a constant, which is 0, plus 2x over 16 minus 56 over 16. So we can simplify this further. So we get x over 2 pi plus x over 8 minus 7 over 2. We set this to 0. So from this we get x 4 plus pi all over 8 pi equals 7 over 2, and x equals 28 pi over 4 plus pi. So when we put this, if we test this out, we get our second derivative, which is d2a over dx squared. That would equal, if we differentiate this again, we get 1 over 2 pi plus 1/8, and this is greater than 0, so therefore it's a minimum.